Okay, now you know what's the challenging part of integer programs, and you also are given a general method that can solve integer programs. Integer programming is still a very active area or research area because there are still so many problems that cannot be solved satisfactorily. Okay, so in the perspective of academia, there are still many things to do with integer programming. But if you are just focusing on business applications, then the following topic is very important for you because as you already can understand, there are many problems that cannot be formulated as a pure linear program. Okay? However, they can be formulated as integer programming problems with binary variables. Okay? Let me introduce this. Let me start with the classic knapsack problem. I have 4 items to select, okay, and they have their weights, they have their values. The knapsack capacity is 10, and then the formulation would be here. I want to maximize the value I get, subject to the constraint that I do not carry more than I can. Each variable is a binary variable. Okay, nothing but a very basic integer program. Now let's add some challenges to you. Suppose I have the following requirements. Okay, I have some restrictions on selecting variables. Suppose we must select at least one item among items 2 and 3 and 4. What should I do? Easy. Now, in this case, it's very easy because these selections has been modeled with binary variables. If among these 3 variables, one of them must be 1, what does that mean? You need to select at least one variable. You need to select at least one item. Once you add this into your formulation, you will select at least one of these 3 items. Sometimes you can select at most a few items, like here. Once you add this constraint, you know you can select at most 2 items among items 1, 3, and 4. So this is a way. These are something you can do. When you are required to do this or not do this, when you are restricted on selecting your variables. Okay? One general technique. There are something more you can do. Sometimes you are required to select item 2 or item 3. Okay? Not very difficult. That just means you need to select at least one of them. Okay? So this can be done. Or select item 2. Otherwise, you need to select both of item 3 and 4. Okay? Either this or that. How to do this? Just a little bit creative. Add a constraint like this, then either x2 must be 1, or if x2 is 0, then they must together be 1. Okay? Now please note that it's still okay to have all of them being 1. It does not violate this constraint. You can even do something like if else. If item 2 is selected, you must select item 3. To do this, you're going to use an inequality like this. Okay? If you select item 2, if x2 is 1, then your x3 must be 1. But if your x2 is 0, you have no restriction on x3. Okay? Or if item 1 is selected, you cannot select items 3 and 4. Then you do something like this. If x1 is 1, the left hand side becomes 0. You can select nothing among x3 and x4. But if x1 is 0, then there is no restriction for you. Okay? If else can also be done. If you are talking about selecting some items, then all these special constraints can be formulated, and they are all linear, right? Okay, now let's do something more, slightly more difficult. Now we will talk about non-integer constraints. We will talk about fractional variables. How do we deal with fractional variables with binary variables? Let's consider the following application: fixed charge constraints. Fixed charge means some fixed payments, fixed costs. For example, suppose you have n factories, one market, and one product. The capacity of factory I is Ki, and you have unit production cost at factory I, which is Ci. Producing one unit requires you to pay Ci. You have demand D. You want to satisfy all the demands by selecting some factories to do the production with the minimum cost. What's new is that now we have some setup cost at factory I. Setup cost means if you don't produce anything, then you don't pay that. But once you produce any single unit, then you pay the full setup cost. You need to pay something to set up, and then you are allowed to produce. Okay, so your setup cost graphically is something like this. If you don't produce anything, it's zero. Otherwise, it's positive. Let's show you how to formulate this problem. I now need the following variables. Xi is the production quantity at factory I, nothing special. And I now need to have a binary variable yi. Yi, I declare it as yi is 1. If some products are produced at factory I, or yi is 0 otherwise, okay? I say that I want yi to be a binary variable, okay? A binary variable, and their physical meanings is here. Objective function is here. Given these variables, I want to minimize my production cost and the setup cost, okay? If I produce something, I pay that setup cost. I have capacity constraints. Xi cannot be greater than Ki. I have demand fulfillment constraints. Sum of Xi must be at least D. The last thing I need to do is to connect Xi with Yi. Okay? Once Xi is positive, I need Yi to be 1. So if Xi is positive, I need Yi to be 1. If Xi is 0, then Yi should be 0. Okay? And the answer is here. To formulate that relationship, all we need is a constraint like this. Xi is the production quantity. Ki is the capacity constraint and capacity, and yi is that integer variable. With this particular inequality, we can connect xi and yi. Why? If xi is positive, your yi cannot be 0. Okay, otherwise you violate this constraint. And if your xi is 0, okay, then this constraint basically is removed. You have no restriction on yi. Yi can either be 0 or 1. But in this case, you obviously see that yi must be 1. Why? Because in your objective function, you are minimizing your total cost. If yi can be 0, your optimization software will set yi to be 0. Otherwise, you are paying some money with no reason. That's not going to be optimal. Okay? So your yi must be 0 if your xi is 0 with that particular objective function. This is not always true, but for this particular problem, it is. Finally, this is very important, so let me put some stars here. You need to tell everybody that your xi is non-negative and your yi is binary. Okay? Every beginner feels that they don't need to do this. Every beginner feels that when they declare the variable to be binary, they are done. No, that's not right. In your formulation, you need to say that yi is binary like this. Okay, if you don't do that, that's wrong. The definition is something to be read by people. But this is your formulation. You need to include this in your formulation. Otherwise, you are not really restricting yi to be binary, and then your program is wrong. Okay? Keep this in mind. Let's look at the fixed charge constraint again. This constraint is known as the fixed charge constraint. In general, something like this. Okay? X and y are decision variables. M is a very large constant. Y is binary. X is fractional. And we can say that X can determine the value of Y. When X is 0, Y is 0. When X is positive, Y is 1. One thing to keep in mind is your M must be set to a upper bound of X, just like here. Okay, Ki is an upper bound of Xi, right? Because Xi, your production quantity cannot be greater than your capacity. So Ki is an upper bound of Xi. This must be done. Your M must be large enough. Why? Because, like here, suppose you write Xi is less than or equal to, let's say, Yi. What's going to happen? You are requiring yourself to that Xi cannot be 2, Xi cannot be 3, which is obviously wrong. If your Ki is, let's say, 100, but here you put 50, that's very stupid, right? You actually can produce more than 100, up to 100, but you are requiring yourself to producing less than 50, less than or equal to 50. That's not right. That's too restricted. So your M here or here must be large enough to be an upper bound of the left-hand side, to be the upper bound of the left-hand side. Then this fixed charge constraint is correct. Okay. In this case, you set it to Ki. You of course can set it to Ki plus 1, 2 Ki, 3 Ki, and so on and so on. Okay. But typically we prefer the upper bound to be as small as possible, because that's going to basically make your feasible region smaller, right? Once your upper bound is chosen to be smaller, your feasible region becomes smaller, and then solving your problem typically gets faster. One particular special case is when your X is binary, then all you need is X less than or equal to Y, because X is binary means X is less than or equal to 1, and then 1 is an upper bound. One question I want to raise here is, look at your previous example about n factories, one market, whatever. What if there is no capacity limitation? Okay, how would you find an upper bound of Xi? Okay, think about it. Okay, there are some more general things that we can do. For example, with the similar technique, we can actually flexibly select constraints. Here, we are selecting some constraints, not selecting binary variables. Okay, make a clear distinction with the binary, the knapsack example we talked about in this course, and what I'm going to do now. We are selecting constraints, not just variables or items. Suppose I give you the following two constraints, and I say, please satisfy one of them. One of them satisfying that is enough. How would you formulate it? I only need a binary variable z, where it is 0 if the first one is satisfied, it is 1 if the second is satisfied. And then let's get mi as an upper bound of each left-hand side. Then all I need is to write the two constraints like this. If z is 1, okay? If z is 1, then in the second constraint you don't have that right-hand side. and that means you need to satisfy the second constraint. But if z is 1, this m1 is very large, and that means this can always be satisfied, okay? Because m1 is an upper bound of g1 of x. Then your first constraint is really redundant. Or if z is 0, then it's reversed. When z is 0, you don't have this, b1 goes to the right hand side, you must satisfy this. Otherwise, or if z is 0 here, then second constraint is redundant. You are allowed to select at least or at most some constraints. If you have 3 constraints here, and you want to satisfy at least 2 of them, then all you need to do is the following. Okay, you set zi to be 1 if it is satisfied, and zi is 0 otherwise. Then we're going to create 3 constraints here. For each constraint is just like what we just observed, right? And when you want to satisfy this constraint, you only need to set zi to be 1. Ta-da! This constraint is satisfied. And you are required to have at least 2 constraints to be satisfied. So among z1, z2, z3, you need to select 2 of them. And once you select 2 of them, you need to satisfy that 2 constraints. Now, this is how we formulate this problem. If you want at most 2, then you can simply change this, right? Sometimes we say that if some inequality is satisfied, then we have this, okay? Satisfy this constraint when this is satisfied. To model this, again, it's very simple. If A then B is just not A or B, a simple logic expression. And then if you want to satisfy this, all you need to do is to negate this statement. And then you want to do either this or that. Or you just want to select one out of these 2. Then you know how to do it. Okay? You know how to do it. So that's our current progress for using binary variables to enrich your LP formulation. All those additional constraints we add into our formulation are linear constraints. Okay, so basically that's why your Cplex allows you to solve it. Your Cplex can deal with linear integer programs, and with those binary techniques we introduced to you, you are creating linear integer programs. Okay, no matter you have if else, either or, at least, at most, or whatever, fixed charge, that's linear integer programs. Okay, during the lecture time we will give you some concrete concrete decision problems for you to see how they can really be used. Or now it's time for you to think about your case study, about that planning problem. There you can do many things with your binary variables, right? Think about it. Okay, let me conclude this video with the case waste management. Waste management company operates a recycling network with many landfill sites, many plants, many facilities, and many recycling plants, many stations, and many collection depots. Okay, and I need to select routes. I need to schedule my vehicles from my plant to go to collection depots and get something back to my recycling plants, and probably going through some transfer stations, and so on and so on. How do I determine a route? The way to scientifically do this is to construct a network with nodes and edges. All these stations are nodes, and the edges are those paths connecting them. And then I need to give each edge a binary variable. 1 if it is included in the network in the route, and 0 otherwise. And then I'm going to create some constraints that resolve, for example, that the selected edge really creates a route, and so on and so on. Okay. What's the key here is you really need a integer problem. You really need an integer program, because you cannot round up or round down your route selection. Okay, it must be 0 or 1. It cannot be fractional. Unlike tables and chairs, this cannot be fractional. Waste management constructed a huge IP to save the company around 500 million over a 5-year period. Okay, simply because you know how to do IP, simply because you apply that technique to this particular planning problem, you can save your company around 100 million US dollars in each year. Okay, then you can create a lot of benefit to your company. Okay, that's the end of our introduction to integer programs. Thank you.